Hello guys and girls. So today I wanted to share with you a little bit about electronics, of course, as I always do. And we're looking at the inside of a 555 timer, of the workings of a 555 timer, and I'll go through it step by step. And what you see here, I have also done on my breadboard, but I want you to know what this circuit does up front. And also I want to explain how the 555 timer works in principle along the way. So as you see here, we have here the ground, and this is the pin 1 of our 555 timer. Then here we have the trigger point. This is pin 2 of our 555 timer. Let's mark a ring around it so we can see better that these are pins 2. And out here, this is pin 3 of our 555 timer. And yeah, pin 4 I don't have drawn here. Pin 4 is just hooked up to high. I do it with 5 volts because it's the reset pin, and it's enabled if it's low. So I just hooked it to high, and I don't draw it here, pin 4. But yeah, so we have 1, 2, 3, and then 4. And then we have the first lower half of the pins of the microchip. Here, the lower half. 1, 2, 3, 4. Now we're going to the upper half of the microchip or integrated circuit IC of the 555 timer. There we have pin 5 first, and pin 5 is really a special pin for sorcering with or doing magic with the voltage level of the 555 timers, but in a regular operation you don't need it. So we have also not drawn pin 5 here, because you can really leave it empty. As you see here, there is nothing on pin 5 here in this row. Then we come, after pin 5 comes pin 6. Pin 6 is the threshold pin. It is this one here. Then comes pin 7, which is the discharge pin. One of these, so I do a 7 here. And then the last pin is pin 8, and that is a very easy one because it's just coupled to, just tied to ground. So that is pin 8 here. Okay, and so we can imagine that these are the pins 1, 2, 3, then 4, 5, not relevant, 6, 7, 8 of the 555 timer. And so let's look at the inner workings. And for that, I think I'll draw a box where the inside separates from the outside of the 555 timer. And I would say that I draw the line from above. I draw it here. So, and then we're here, down here, the separation line should be, to best visualize it, I think it should be here, yes. So if you look at the timer from above, you see this black integrated circuit IC here, this with the 8 feet, 8 metal pins, 8 metal feet. That is the inside of that chip here. And so I start with explanation here. So this is the pin 8, the VCC pin. Pin 8 VCC here. This one we draw to VCC. And VCC, as you know, perhaps I draw it in red. VCC, that's in my case it's plus 5 volt, and there is just simply plus 5 volt coming into the chip from the outside. VCC, we tie the pin to a power source. So perhaps I draw it here like this. Here would be power source. That is, the plus is connected to here. And then you have directly VCC coming in here. Then we follow this path from VCC, and the question is, okay, where do we follow the path to? We go down through this resistor first. Just don't mind the things to the right here. Then from the power source plus through this first resistor, then through the second resistor, and then through this third resistor. So, and then we are at ground down here. We have to have a nice color for ground too, shall we? Yeah, so ground is black, so it's already there. And also these things here also are ground. So one time I wrote it as ground, and then you have also these grounds here, and here you have a ground, here you have a ground. And then let's say we come here in with, just for the sake of it, with a 9 volt battery now as an example, because it calculates very easily. Let's say we have here plus 9 volt, even though I will be doing it in practice then with 5 volt. That's the cool thing, you can do it with any voltage nearly here, but let's say we do it with 9 volt. And then if you come here in with 9 volts, and you there is of course current flowing from this plus 9 volt to ground, and then current flows through the first resistor, so you have a voltage drop here. Current flows through the second resistor, you have a voltage drop then across this resistor too, and then current is flowing to ground through this third resistor. Of course you have 3 voltage drops, so 1, 2, 3 voltage drops. And because these 3 resistors are equal in size, you have the voltage drops to the same amount across every resistor. So voltage drop 1, voltage drop 2, and 3 are equal, so 3 drops. So you can imagine that 3 equal voltage drops from 9 volt to ground to 0, that each drop is 3 volts. So here we start with 9 volt. Then what's left now here is after the first resistor we drop 3 volts. Then we have 6 volts here, 9 volts here, 6 volts here. Then we drop another 3 volt across this resistor. Then we have 3 volts here, and then we drop the last 3 volt until we are at ground or 0 volt. We can write that again, but this is trivial. Ground is 0 volts. Everybody knows that, don't you? I can make a video about this. It's complicated. Not so bad here. Okay, so baseline, what have we learned or found out? So that we know now that we are here and on this line, and consequently at this strange minus of this device here on the minus side, we are at 6 volt. There's a 6 volt here. Then at this device, and I tell you, these are operational amplifiers, op amps, but that doesn't matter so much. Just follow me along. We'll come to that later. And we have at the plus terminal of that op amp, we have 3 volts. So at the minus here 6 volt, at the plus terminal of the second op amp, 3 volts. And yeah, and that's about the first thing you need to know. The first very basic, very important thing to know, that there is this voltage divider with 3 resistors, and that we divide the voltage by 3, and that we feed the 6 volt and the 3 volt or whatever is a third of the initial voltage into the op amps in this way. The first amp on the minus, the second one the plus. And that makes no conclusion as of now how we going to use that, but it'll all become clearer now. So because first focus please on this op amp here to the lower side. What do we do with this? As you see, we have on the external side, because we're on the outside of the operational amplifier. You see here's the boundary, we're on the outside. What have we done? We have tied this pin 2 here of the 555 timer pin 2, which goes to the minus of the second op amp. What have we done with this? We have tied it to VCC. So VCC here, so meaning in our example it is at plus 9 volt through this resistor. There, tied to plus 9 volt. There is here an open switch, but we don't have to care about it because it's open. That means nothing for the moment, so we can skip that part, this open circuit here. Just know that when this is tied over the resistor to plus 9 volt, then this minus terminal here of this second op amp, it is also tied to 9 volt. And I tell you, if you don't know yet, these are the inputs to the op amp coming from the left. I mean, it's a little bit obvious. These inputs here from the inputs often are drawn coming from the left, and these inputs of the op amp, they eat or no current, or they sink no current. So there is no current flowing into this op amp. So we don't have to worry about any voltage drops here across the resistor, because there is no current flowing here. And if there is no current flowing through the resistor, so then there is also no voltage drop. That's a simple Ohm's law. Perhaps in another video of mine you've seen it, or I'll make a video about it. Only when there is a current flowing through the resistor, there is a voltage drop across the resistor. When there is no current flowing, then there can be no voltage drop. So we don't lose any of the 9 volts across this resistor. 9 volts is also on the other side of the resistor, because there is no current flowing in here. And then we have 9 volts all the way. Also 9 volts are here at the minus terminal. And that is the first significant thing to note. Here we have, in the initial state, like we have drawn it, we have 9 volts here. And now let's see the situation. The 3 volts are at the positive input of the op amp. The 9 volts are at the negative input of the op amp. And how does this op amp now behave? What does it output? How many? Op amp always outputs voltages. In our case, it could output every voltage from 0 to 9 volt, because what you have not drawn, and it's often as simplified as that, is that of course these op amps are internally connected to VCC and ground. But that's a secret, oftentimes not drawn explicitly. No? People always think of it as a given. And so the op amp can then output, that's also kind of the supply voltage of the op amp, and it can output here at the output terminal of it to the right, at the peak to the right here of the triangle. It can output anything between ground 0 volts or 9 volts. And so what does it output? And the secret about an op amp is, if you do it in such a way, like I have drawn, so only inputs and no kind of feedback circuit or anything complicated, then it's always the simple rule: whatever terminal has the higher value, that extreme of the supply voltage is output. So meaning here we have 9 volts at minus, 3 volts at plus. So who wins, minus or plus? 9 volts at minus, 3 volts at plus. Yeah, of course, minus wins. 9 volts is clearly the winner. It is higher than 3 volts. So if the minus input is the winner, then the extreme low of the voltage supply is output. So our extreme low of the voltage supply of the op amp is ground. So we put out 0. or low. So let's draw this perhaps in green. In this or let's make it red colors for this initial configuration. So 0 volt is output. Because 0 volt, because that's the lowest we can output here because of supply of the op amp. And we output why do we output the lowest we can have? Yeah, because the negative input wins. Because winner is the one with the higher voltage here, 9 volt. Okay, there are 0 volts output. So this means logic for this circuit here, and I tell you it is an SR latch, so-called, but you don't have to worry about that. It just means that this input here of this SR latch, it gets 0 volt, or how do you say low? We say low to 0 volt in this case. In 9 volt or our high. Yeah, that's pretty straightforward for everyone being ever involved in anything digital logic things. You have a high and a low. High means 1, high means high supply voltage, and then you have a low. Low means 0, or low means the lowest voltage you can have. So our low is 0 volt. And yeah, so we have a low here at the set. S for set input. I can also write it down. Set input, and then R is a reset input of the SR latch. Yeah. So what happens? A low input at the set, low on set. So we tell set, hey, be low. Don't do anything. Do nothing, please. Oh, and set, oh, okay, I can do that. Nothing. Do nothing. That's feasible for me. Okay, I don't set anything. So you don't do nothing? Yeah. And then, oh, boring. Okay. Yeah, boring. Okay, nothing happens. Yeah, boring. It's boring. Okay. End of story. Okay, so nothing happens down here. All right, okay. Then we could also, what could we inspect next? Because nothing is happening down here. Then we could inspect, yeah, okay, what's with the upper op amp? Is there some party going on up here? Because we want to have party, we want to have electrons flowing and such. So we want to have party circuits, not boring circuits. And let's see what happens up here. So, what is the case up here? So we have, we look here, we have 6 volt. We also derived that the negative input terminal of the op amp is 6 volt. Of course, we have also the 9 volt here. Let's draw it to be consistent. Check, check, check. 9 volt in the ground on the op amp, implicitly assumed. And here we have a power source, 9 volt. And then we have a resistor here. And then, oh, we have a fork. One port goes here and one port goes here. And I tell you, for the moment, we have to make some assumption. And we'll come back to that later. But the big question is, okay, we can now follow this path. And we can follow this path. And if we follow this path, things are quite clear. We have a connection from 9 volt to this plus terminal. And as I told you, the op amp is not here in this left input of the op amp in the plus side. There is no current going in because the op amp doesn't sink current. No, it's high impedance, so-called, very, very high impedance, so it doesn't sink current in the ideal theory, and we assume that ideal theory now. So it all depends. The same voltage level we have after this resistor, because there is no current flowing in here, we have just the same voltage on this plus terminal. And the big question is, okay, what voltage is here after the resistor? And that really depends on, is current flowing through this resistor or not? Because if there is not current flowing, we simply have 9 volt again here and then 9 volt here. end of story. But if there is current flowing through it, then there could be a voltage drop. And now, so he can flow no current, so here we said we don't, this branch down here, we don't have to inspect because we know there is no current flowing. But the question is in this path, is there current flowing? And the thing is, okay, here's a capacitor. Yeah, okay, if we're talking about DC current, there cannot be a constant current flowing DC through a capacitor. It charges up to some kind of full state or something, and then it's over. So we don't have to inspect this capacitor for now. It's also coupled to ground here. This is just 9 volt coupled to ground, and this capacitor will charge up to 9 volt, and then that's it. Perhaps there will be current for about some time flowing, but it will not be a long thing until it's 9 volt, and then there's 9 volt also here. But let's look at how this continues. There is this discharge thing here. Okay, this discharge pin, and we are connected to it. And what is this? Okay, this is a transistor. So transistor here, and it's, yeah, I don't know, it's an NPN type. But you don't have to have the details about transistor NPN type. What is this? You just have to know that a transistor, we can see a transistor as a switch. And the transistor can be an open switch, just like the one here, an open switch where no current can flow through. It can be an open switch, or it can be a closed switch. And then if it's a closed switch, it acts nearly as if it's just a conducting line where there's no resistance, where just current can flow easily through. So this transistor can be one of two states we can think of. Either it's just like a connected line to ground, where current can flow through happily and without much resistance, nearly no, so we will assume no resistance, happily flowing through, or it's an open switch, and it's really a hot break of the circuit here, and nothing can go through, no current can go through. So either an open or a closed switch, this transistor. And the cool thing about this NPN transistor is it is closed so that's a detail. It is closed, so the switch is closed and current can flow through. When we have plus here at the base, this is a so-called base, the controlling line, base, when you have a positive voltage here, and it is closed when we have ground here. So it really depends, and we don't know yet. Is this point here after this strange SR latch, and we don't know yet what is outputted here. And so I tell you, this really depends on how, as we will see later, there has to be some initial state of this SR latch on the output here. And that's just when you switch the IC, when you connect the IC to power, there has to be some kind of state here on this SR latch. And we'll just assume, let me think of what we assume. We could assume that this is the output here, the output is at pin 3. We could assume that the output 3 is high, so 9 volt in our example. And if this would be high, then plus 9 volt we would have here. Then we would have a voltage drop across this resistor and this light emitting diode, and then this diode would light up. So I have here the light emitting diode. Just for sake of it, we can just check that. What happens if I switch on this concrete circuit here? Is the light lighting or isn't it lighting? So I could not make rough guesses. So now I connected the power and it's not lighting, okay? So, and if I now hit that button, Okay, it's sliding and then it goes off. Sliding and let's go. But on the initial side, I'm disconnecting power again. And I'm reconnecting power again. Nope, it's not lighting. So we can assume, don't let me trick you, just always take the real word for it. So we can assume that there are on the output here 0 volt. And okay, 0 volt, then no 0 volt from here to 0 volt here. This means no voltage drop across the LED and the resistor, so of course the LED doesn't light, as you have seen. What is this thing here? It is an inverter. You see that with the little funny nubble here, not filled with black paint, but just a circle. And an inverter means what is going into it at the input here is just inverted, and the opposite comes out on the output. So since we have here on the output side 0 volt, the opposite must have come in. The opposite of 0 volt, so 0 volt is low, so high must come in. High come in, low come out. So there must be high at the input, and high is our 9 volts. So there must be 9 volts initially here. Okay. That means, as I told you, when we switch on the circuit here is 9 volt, obviously. We derive that from the output where there's no volt, 0 volt. And because there is 9 volts, this transistor is on. Because 9 volt is at the controlling terminal, the base of the transistor, then this is on. So this means this is a conducting line here. Conducting line without any resistance, current happily flowing through it to ground. And what does that mean? That means that we have here 9 volt, here this resistor, and then a line and happily throwing through to ground. So this means there is a voltage drop and no current flowing, of course, this way, because an op-amp doesn't sink current, as I told you, and the capacitor also not so much. So we have a pretty stable state that there is the whole voltage, the whole current flows through this one resistor, and the whole voltage is dropped through this, over this one resistor. And we end up in the initial state, because this transistor is a closed switch, that we have here 0 volts at this terminal. What does that mean? 0 volts for our input of the op-amp, where there is, of course, if here's 0 volts on this pin 6 threshold input, it's connected to the plus input, then of course here's also 0 volts. 0 volts. That means, now we can again ask us about this op-amp. Which input terminal is the winner? Plus has 0 volt, minus has 6 volt. So minus is the clear winner. And if minus wins, the minimum supply voltage is output. The minimum supply voltage is ground. And ground is 0 volts. So this thing here also outputs 0 volts. And this op-amp. And yeah, 0 volts is low. So low meaning telling the SR latch on the reset input here, low, do not reset. How boring is this? So we don't tell, down here we have low, we don't tell the IC to set anything, and we don't tell it to reset anything. That's pretty boring. So there's nothing happening. Low and low on the input of the SR latch. So basically, or low and low, or in our binary language, 0 and 0 input to it. And what does such an SR latch do when it has don't reset and don't set anything as an input? It stays the same. It doesn't do anything. It doesn't change its output. And as we've seen on the switch on, the output must be 9 volt here. So 9 volt on the output. And basically now it's time a little bit to talk about this SR latch. What does this Q and not Q mean? Because really, I tell you, this Q is the real output of this SR latch, but it doesn't go anywhere. It's a dead end. Here's Q input, output, just Q output. But what is really output, you have two outputs at the SR latch, and Q, which is a real output, and then a Q bar, which just outputs the inverse of anything that Q outputs. So if Q outputs 1, Q bar outputs 0. If Q outputs 0, Q bar outputs 1. It's just the opposite. It's like a nagging child. So you say yes, I say no, blah. That's just the relation of Q and Q bar. It's just inverted. And so I have to tell you a little secret. Maybe you already know or not. This output of the SR latch, so where does this 9 volt come from? Does it come from Q or from not Q? It comes from not Q, from the inverted output. Perhaps I signal that in such a way it's not cool drawn, but yeah, just to let you know. Q goes nowhere. This SR latch outputs from Q bar. So we have to just take it as it is. The input side of the SR latch, with all of our magic here, it tells the SR latch do nothing. And if it's do nothing, the SR latch just stays as it was when switched on. And its switched on state was, obviously, because the light did not shine here, that it had 0 at the output, meaning 9 volt in front of the inverter. There's just a derivation, must be. Light not lighting 0, then there must be 9 volt, and there is 9 volt, that's a reality. Then that transistor must be on if this is 9 volt. And just another reality, where does this 9 volt come from? It comes from Q bar. You cannot do anything about it. It must be so. It is wired so. The constructors of this circuit have done it so. 9 volt come from Q bar. Eat it. You can't change it. You think it should come from Q? No, it comes from Q bar, this 9 volt, and that's reality. That's the initial output side state. We cannot influence on switch on of the circuit, we cannot much influence the output side. It's just the way it is. So designers of the circuit, they said, okay, if you switch it on, then the output side is like this. And all we did is we analyzed a little bit, okay, is it on or off or what? And the input side says do nothing, so here. Okay, now it would stay forever this way. As you see, this thing does nothing. This thing does nothing until we do something, and perhaps hit the button. And what does it do when you hit the button? So we could wait here. I'm in my 30s now. We could wait until I'm in my 90s or 80s or something. Nothing would happen. This thing stays as it is. It does do nothing. And if you press that button, only if I decide no, yes, no, yes, no, yes, no, no, it doesn't do anything. Now I press the button. And now the light goes on for a small time of like a second or a little bit more. And then it goes off. And then it does nothing. Until I'm 80 years old or such. Nothing. Till I press the button. And then a second, and then it goes off. And that's the purpose of the circuit. Okay, button pressed. A second, then nothing. Button pressed. Okay. If I do nothing, it does nothing. Okay, and now the question is, okay, how do we get this circuit that does really nothing? How do we get it to do anything? And as you've seen, the magic formula is that I press this button here down. We connect this thing here. We make it from the open state, this button, to the closed state, and then all the magic happens. And let's do that now virtually. Let's do this in green color. So by drawing green here, this connecting line. once the button is down. Oh, I think green is not the best color, is it? Perhaps we'll go with something else. Can you see, like, yeah, orange seems pretty decent. Or perhaps blue, or this lighter green. Yeah, this lighter green, but blue is also cool. I think I'll go with blue because it's the most visible here. No, okay. Now perhaps the lighter green is even better. Yeah, I think the lighter green is better. But orange could also be good. I go with the light green. Okay. So now this switch is closed anyway. Our rainbow switch, it is closed. And now that this switch is closed, there happens an interesting thing. Because the VCC here, there's no current flowing to the input of the op-amp. But now there can be current flowing directly to ground here. And that happens. And so we have here all the current flowing through this resistor to ground, and we end up with 0 volts here in the green state, in the trigger press state. And when we happen to have 0 volts here, after the resistor, we also have 0 volts here instead of 9 volts. And when you have here 0 volts, we have to look the winner situation again, because who wins now, minus or plus? In the red state, with the button off, the negative had 9 volts and was the winner. Now, because in the green state, of course, we don't change anything here. There's again 3 volts. We don't change the voltage divider. Now the winner is the plus. Okay, so plus is the winner. So meaning this thing doesn't put out 0 volt. This thing puts out 9 volt. Okay, high. So we press the button, it's closed, and then for a certain kind of time when the button is down, is closed, then the 9 volt are output here, or high. And this tells again this thing to set. And what does set mean? Set means on the regular output a 1, or 1 meaning 9 volt, high, 1, 9 volt, 9 volt, 9 volt. And if at the Q input 9 volt is output, what does not Q, the little nagging child, do? Of course, the opposite. So 9 volt Q, not Q is 0 volt outputting here, 0 volt. And this output of 0 volt, oh, before we had 9 volt as output of not Q, now we have 0 volt at output. Okay. And now we have to inspect both sides here. But let's inspect first what happens on the lower side. The lower side says, okay, I have an inverter again. So your 0 volt you're inputting to me, I'm an inverter. I'm a little nagging child. I do the opposite. So 0 volt. So I'm outputting not the opposite of 0 volt. This is 9 volt at the output. And because there is 9 volt at the output, then we have a voltage difference over the resistor, over the LED, down to ground, 9 volt to ground. Now all of a sudden there is current flowing through here. Current, I. For I output, they often use. And this LED, it shines. Yay. So that's the downside, the lower side of the circuit. From this point here, spoken from this point here, what happens on the lower side? On the lower side happens, the LED is on. Okay, that explains when we do this, click, it goes on, but it goes off. And there must be something that forces this thing to somehow go off this LED again. And that we'll see when we look at the upper part of the circuit. And yeah, we see now that formerly we had this 9 volt. And so we said on the input of the transistor, and the transistor, it was just on, so as a closed switch. But now we have 0 volt, and now this thing is off. And it acts, when it's off, it acts like an open switch. So no current can flow through here anymore, through this transistor. Okay, no current can flow here. Oh, what does that mean? That means that now all of a sudden, if no current flows through this resistor anymore, in such a way, then no current is flowing through this resistor, then there's no voltage drop. We don't lose voltage. We don't drop voltage over this resistor. So the 9 volt that are here, they would also be here, the 9 volt. But I tell you, it's not immediately so. So we first had 0 volt here. So if we draw the 0 volt, that the 0 that are here, of course, we had the 0 volts here and the 0 volts here. Everywhere on the line we had 0 volts before. And also here the 0 volts, you see, we've drawn it on the input of the op-amp. But what happens now? We do not have immediately the 9 volts here, but there is an interesting thing happening, because we had 0 volts here over the capacitor, 0 volts here and 0 volts here. There was nothing happen across the capacitor. But now, as this path here is disconnected, the switch is open, because we have a 0 volt here that opens the transistor as an open switch. Now, if we wanted to have spontaneously 9 volt here, the capacitor would say, oh, hey, there, or if we have a moving towards 9 volt, the capacitor says, hey, I can take some of your electrons, and I can save, I can store some voltage. That's the thing that the capacitor does, and it notices, okay, there is some voltage going up. I can store some of the voltage. And the pretty thing is, oh, not the pretty thing, but yeah, in this case it's really useful and pretty. If you have a resistor in front of a capacitor, so here 9 volt, then a resistor, then a capacitor, then that is called an RC network. So R for resistor and then C for capacitor, you have an RC network somehow. So 9 volt in a capacitor. And the capacitor then, if you have to do it over a resistor, then the capacitor node, it doesn't go immediately to 9 volt. Why not? Because the electrons, in order to have 9 volt here, positive 9 volt, there have to be first electrons flowing to the capacitor to load it up, to bring it to voltage. And through a resistor, there cannot be infinite many electrons flowing. So a capacitor could only go to 9 volt in 0 seconds, or in a very small amount of time, if electrons would be able to very quickly flow into or flow out of this capacitor. Really, because if that's the positive side here of the capacitor, the electrons will go away here and flow through 9 volt, and they cannot do like immediately go out, and now we're out, and now you have 9 volt. But the thing will be that because of this resistor, they will take some time. There will be a time delay until all electrons are out here and the 9 volt are then there. And that's really what an RC network is about. You have the R and the C. The bigger the resistor, the bigger the R, the longer it takes for the capacitor to get rid of its electrons and for electrons to flow, because a resistor is basically a limiter of current meaning electrons that are flowing. So it will take some time until this capacitor is at 9 volts. And the cool thing is you can control via the values of the resistor. So resistor has 10 kilo ohm or 1 kilo ohm or anything, and the capacitor has 10 microfarad or 100 microfarad or whatever. And by controlling the R value in ohms and the C value in farad, you can control the time it takes for this capacitor to get rid of its electrons and the time it takes to get up to 9 volt. And so you have to choose these things deliberately, but the only thing is you change the time it takes, but it takes some time for this capacitor to get to 9 volt. And also, of course, what this capacitor does, it goes gradually up. So first there is 0 volt here, then we disconnect here, zack, because we have here the 0 volt output all of a sudden, because we have the trigger closed. Then zack, we have 0 volt here, zack, the transistor is an open switch. And then, oh, the capacitor says, I start charging up to 9 volt here. And it takes some time, and it will get to 1 volt, and the capacitor will get to 2 volts, more electrons flowing out, it will get to 3 volts, get to 4 volts, or 5 volts. And what we're interested in, at some point in time, this capacitor will get to 6 volts, and then to 7, and then to 8. But we are interested when this capacitor is at 6 volts. Why so? Why is 6 volts so interesting? Yeah, because when this capacitor is at 6 volts at this side, then the potential on this side is 6 volts in reference to ground. And on this whole line it is 6 volts, the potential. And as you see, when this potential is 6 volts here on this side of the capacitor, also the input of the op-amp is 6 volts. And then in just a fraction of time, in some small amount of time, it will get to 6.1 volts or 6.2 volts. And when that time comes, when this input is 6 volts and then it gets slightly above 6 volts, 6 point something, 6.1, then all of a sudden, before here in the red state, the 6 volts was the winner over the 0 volts, and the minus was the winner, this output 0. And then all of a sudden, when we get to 6 volts or 6.1 volts or higher, all of a sudden plus input is the winner, not anymore the minus input. If the plus input is the winner, this thing starts outputting high. It starts outputting 9 volt. So let's draw the situation, let's say just 6.1 volts here. The time when we have 6.1. It takes some time. Let's call this time it takes to get to 6.1 volts time. Time to 6.1 volts. Let's call it it's charge up time of the capacitor. Let's say this, how long, let's say this takes around 1 second. Let's call it 1 second. So let's say we have the resistor and the capacitor such that it takes for the capacitor to go through this resistor to 6.1 volts. Let's say this is 1 second. And then after 1 second, this thing goes to 6.1 instead of 6.1 volts. 6.1, hopefully you can read it. Instead of 0 volts, then all of a sudden the plus terminal is the winner, and this op-amp outputs 9 volts. And then this thing here says reset. And reset means, okay, reset says the Q output, the regular output, shall be 0 volt. So perhaps I draw this in orange now, because we have orange, let's say now, we have 0 volt that shall be output again. And then, when Q output 0 volt, what does not Q output? Yeah, the opposite. So 0 volt, then this means the not Q outputs 9 volt. And 9 volt, we're back again at the initial situation, outputting 9 volt, meaning the child, here again 9 volt, meaning the inverter child here again says 0 volt, ups, and the light is off again. And now it all makes sense. It took 1 second after pushing the trigger, when pushing the trigger caused this thing here to go, the switch to go open, and then it took 1 second until the op-amp was fed with 6.1 volts and higher, until this reset hit, until 9 volt here established again, and then the light goes off again. So what we really do by pushing the trigger is we, for some small amount of time, for this 1 second, the system goes into a state where this light is on for a second, but then the capacitor charges up and this reset pin here reverts all the things, and we're back again with a light that is not lighting. So with hitting the trigger, we just put the thing on for 1 second. And that's really the whole explanation. You can, just for completeness sake, you can say, okay, 9 volt being also here again, meaning this transistor is also with a closed switch. Closed switch meaning current easily flowing through. Again, the situation of the voltage drop, 0 volt being here. 0 volts here means 0 volts here. This thing, negative is the winner, there is 0 volt also here. So 0 volt means do nothing, do not reset, and we're back in the initial stable state. And that's a lot of things to grasp I know. So what along the way, we had inverters, we had an SR latch, we had an op-amp, and the op-amp with one input fixed in this configuration is also called a comparator. And we had voltage drops across resistors, we had buttons, momentarily buttons, we had capacitors, we had RC circuits loading up a capacitor, we had transistors, and we had LEDs and everything. And this is really, the 555 timer. It's kind of a masterpiece, but it's also quite understandable if you get some of these basics. And I think I make some videos also about these basics. I have videos uploaded on my Tinkering Online channel about op-amps. I think I make one about SR latches. And I have one about a transistor, and I have one about an inverter, but I'll do additional ones. And you can always please subscribe my channel, Tinkering Online, and I'll try to make videos all about this, that we learn this stuff together, and it's really fun. But now you know how to make a circuit that acts in such a way when you just close a button for a certain amount of time, that goes for a certain amount of time in the output to high, and then it goes back to its stable state of low. So low is the stable state. You see the light is not lighting. Low, its stable state is low. So and you put it momentarily for a certain amount of time. You put it in its not stable state, high. So see, high is only stable for a second, and then it's low again. Low is the stable state. And you call this kind of circuit with the 555 timer also monostable, because mono means one in, I don't know, is it Latin, mono? Could be, mono, and monostable because it's only stable, single stable on low, monostable, and the other state of being high is not stable. So it's not two-sided stable, it's monostable on low. Only low is the stable state. The other state is no stable state, the high state, but it's temporary state where the system goes out of easily. So I hope you liked it. I can make a photograph of the wiring and such, but it's really only what I have drawn down here. And just for the monostable thing to draw, this means, so if we have here a logic 1, which means 9 volt and plus 9 volt in our case, and if we have here logic 0, which means 0 volt in our case, if it's such a diagram, then this means that your voltage will be at the low all the time. Then you click the button, it goes high for around a second or such, or as you adjust your RC network, how long it takes for the capacitor to go up to 6.1 volts, or a little bit higher than 6 volts. For this amount of time, we'll stay high for 1 second, and then it will stay low until when you do nothing. So this is the stable state of low, so to say, and this is monostable. Sugar. So if I said anything wrong, or parts can be improved, or things can be achieved in another way, or anything, please leave me a comment. But I'll would like if you would hit a like button if anything was of use to you, or if what's cool or interesting. And yeah, subscribing is also a good thing. Take care, and we'll see more of this stuff. I hope you like. Bye.